So let's take a look at the following reaction in which we're basically replacing the hydroxyl group attached to our anomeric carbon, carbon 1, with this amine group. So we want to basically develop the reaction mechanism by which this reaction takes place under basic conditions. So we have our amine as well as our alcohol. So let's begin by redrawing the chair conformation of beta d-glucopyranose with the Haworth conformation. So that looks something like this. So we have our primary alcohol. The H here points up, OH points down, OH points up, H points down, up, down, up, down. So this is the Haworth form of beta d-glucopyranose. So the entire reason I'm using this is because it's easier to draw than the chair conformation. So we know that anytime we have a cyclic sugar, the cyclic sugar, whatever it is, in this case a glucose, will exist in equilibrium with its open acyclic counterpart. So let's draw the open acyclic counterpart. The main difference will be, in this case, in a cyclic case, we have the hemiacetyl group, so the hydroxide and the OR, and this will convert into an aldehyde group. So this will be replaced with an aldehyde group in the open case. OH, OH, H, HOH. So here, this will be replaced by our double bond between the carbon and our oxygen, and we'll have an H here. So when we're in the presence of the base, this base will basically act as a nucleophile and attack this carbon of the carbonyl. So remember, the carbonyl is a pretty good Lewis acid under basic conditions, and the base in this case, our amine, will act, the ammonia amine will basically act as a nucleophile. It will attack this carbon of the carbonyl, displacing the pi bond, placing the 2 electrons onto our oxygen. So we form this intermediate that looks something like this. So we have, let's draw it this way. We have the H here, the N, H, H, H. Here's our oxygen. So notice that we have a negative charge here. We have a positive charge on here. And let's also redraw the other groups that we have here. Okay, so this is relatively unstable because we have a positive charge on the nitrogen and a negative charge on this oxygen. So basically we have a transfer of an H taking place. Because we have a closeness between this H and this oxygen, what can basically happen is this oxygen grabs one of the H's off of our nitrogen, placing the 2 electrons onto our nitrogen, removing these 2 charges. So we basically form this molecule that looks something like this. We have our OH here, this primary alcohol group that points up, the OH here points downward, OH here points up, H points up, OH points down, and then we have this OH here. Our NH2 is now located here, and the H is found here. Now, in the next step, we basically have an elimination step. So because we are under basic conditions, what happens is these two electrons kick off this hydroxyl group and basically form a pi bond between this carbon and this nitrogen. So we form the following intermediate. And H, and of course we have a positive charge on this nitrogen here. Now let's draw our OH methyl group. OH points downward, OH points up, OH points down, H points up, H points down, and H points up. Okay, and there's also an H here that we did not draw. So we have a positive charge on this carbon, on this nitrogen. In the next step, we have a base that is present in the mixture that deprotonates this H. So we have a base, let's say this ammonia, that acts to deprotonate. And in this step, we form our molecule known as the imine. So we form this molecule here. OH here, H goes up, OH goes down, OH goes up, H goes down, H goes up, OH goes down, and this is our imine intermediate. Now, this imine is the open form of this closed form. So in the next step, we basically have the following reaction taking place. We have a closure of this ring to form the 6-member ring. So in the next step, because we are under basic conditions, we basically have these electrons act as a nucleophile, attacking this carbon, displacing the pi bond, placing our 2 electrons onto this section here. So let's suppose our ammonia acts as a base. It takes away this H atom here. So in the next step, we basically form this ion here that acts to close this ring, and that kicks off these 2 electrons, placing them onto this nitrogen. We also have the other groups, so this one points up, down, up, down, up, down. So we close this ring. Okay, we have our NH that contains a negative charge. And so in the final step, we have the ammonium that was basically formed in this step. So when the ammonia took off this H, it formed ammonium, and that ammonium can basically protonate this nitrogen to form this final product here. So our final product looks something like this, which is exactly what this molecule here is, except this molecule is in the chair conformation. This here is in the Whole-Worth form, which is easier to draw, and that's why I used it. But if you'd like, you can convert this Whole-Worth into the chair conformation, and you get the same exact picture as here. So this is this molecule here. So this is the reaction mechanism. And the most important part to see in the reaction mechanism is because we're under basic conditions, the first step cannot be the protonation of this oxygen to go on and form our imine, but the first step is because we are under basic, this acts as a nucleophile, attacks this carbon, and then this is protonated either by, let's say, this alcohol here, or it's protonated in an intramolecular fashion because of the close proximity of this hydrogen to this oxygen here. So we form this molecule, and this hydroxide is kicked off, even though it's not that good of a leaving group because we're under basic conditions. So we form a hydroxide that we did not show, as well as this molecule. And then either the hydroxide that is present in close proximity deprotonates this H, or we can say the ammonia, if it's found in close proximity, could also deprotonate the H to form this imine. And in the next two steps, we basically have a closure of the ring that takes place to form this final molecule, the product of this reaction right here.